I'm a little rusty, but I think I still remember how to single point cut threads. Oh, fuck. Hello, Internet. My name is Quinn, and this is Blondihacks. Today I'm going to finish up the dividing head / indexing fixture thing for my shaper, and we're going to find out if this was worth a couple of weeks of effort or if I should have just broken down and bought the gear cutters for my mill. Let's find out right now. When last we left our Intrepid indexing device, it looked like this. We've got the frame roughed in and that main bearing that goes through the middle, and now I just need what might be called the spindle or the axle or whatever you want to call it. Does the work holding, does the spinny bits. In the previous video, I explained how that work holding collar is going to work, and then the right end of the shaft is a copy of the Vertex rotary table shaft that the indexing plates and crank are designed to attach to. One feature of note is this locking collar that's on the Vertex table. It's got a spring washer behind it, and this holds the shaft in place and sets a little bit of preload on it. Now I need to do something like that as well, and my thought was I'm going to use an M12 nylock nut for this. It's an M12 thread on there, and I happen to already have a nylock nut for that in stock, so I thought I'd try that and maybe that'll work. Ideally, I would use a fine thread M12 there, but I happen to have a coarse thread M12 nylock, so I'm going to use that, and I'm sure I won't regret it. The shaft is going to be made from this piece of round bar, which is quite a bit oversized, but it's the one I have. And I'm going to put a center in this after, of course, facing off the end, as is tradition. I'm going to pull this all the way out and set it up with tail support because much like the main bearing in the previous video, all of the important features of this shaft all have to be done in a single setup for maximum concentricity. Any tiny errors in this part are going to get telegraphed into every part that I make with this indexing fixture for all time, so it's worth the time to make this thing as good as I can. I'll start by turning down the excess, which is, well, really putting the subtractive in subtractive manufacturing. That thing got pretty warm. There was a lot of material to shift on this one, but I finally got down to the outermost diameter of the part, which is that collar that seats in the thrust bearing. Next, I turn down the work holding collar at the far end. This needs to give me just enough wall thickness for a good amount of threads on the work holding set screws, but the smaller it is, the more clearance the shaper tool has for tool runout room. So there's kind of a balancing act there. Now I'm going to turn the back side of that flange, that thrust flange, and I'm going to do it with left hand turning. So I'll cut a groove at the chuck end of the work to give myself a starting point for the left hand turning tool. Since again I want to do this all in one setup, I want to be able to face a nice accurate shoulder on the back of that flange. So doing it all with a left-hand turning tool is an easy way to do that. I did some facing cuts on the back of this flange to bring it to final thickness. I want this to be very accurately square to the rest of the shaft. And that's also going to need a little bit of an undercut to make sure that it's sitting firmly against the thrust bearing. Remember, the collar, the bronze collar that goes around this, acts as radial and axial thrust. So I really need to make sure that this flange is able to sit firmly back against that thrust surface. This shaft needs to be as accurate and high quality as I can possibly make it. So I've got my best micrometer out and I'm taking measurements all the way down. There's a couple of tenths of taper in it, which normally I wouldn't care about, but I've also left it a couple of tenths oversize so that I can bring it down with the Model Engineer's surface grinder, which is, of course, emery paper. I want this to be as perfectly accurate dimensionally as I can get so that it'll run smoothly in that bore with as perfect concentricity as possible. And of course, it can't have any play in it, which would cause a loss of rigidity in the setup and also cause concentricity issues. So bringing it into final dimension and eliminating any taper with emery is time-consuming, but worth the effort here. And I gotta say that really paid off. This thing is dead nuts perfect on dimension and zero taper within my ability to measure, which in this case is a tenths micrometer. So I'm less than a tenth dimensionally and on taper. And that's as good as I can make anything with the equipment I have. So I'm very happy about that. And of course, chamfers are what separate us from the animals. Now it's time to do the work holding collar, but of course, again, all has to be done in one setup. So out comes the tailstock, in comes the steady rest, And this time I want to be extra careful in setting up the steady to make sure that I'm not affecting the concentricity or the squareness of the bore that I'm going to create. So after I set the rollers by feel, what seems about right, I'm then going to get out the dial test indicator, and I'm going to ensure that I haven't deflected it or caused any other issues with those steady rollers. Running the DTI lengthwise along the top, I can see that indeed the steady is pushing the end of the work up by a little bit, by a few tenths. So I'll back off my locks on these rollers, and I'll lower the lower rollers down a little bit, and I'll push the upper roller down a little bit until that's running 0 all the way down the shaft. And that looks perfect. Then I do the same check on the horizontal plane, and in that case no adjustment required. That's running 0 all the way down already. And then one more sanity check. I'll check concentricity at the end. This is a little bit of a false indicator because all it really tells you is how good the rollers and the steady are running. It doesn't tell you if the part has been deflected by the rollers being incorrectly positioned, but it makes me feel good. All right, that's running perfectly as far as I can tell. So now I'm going to remove the bulk of the material with a pilot point drill. That's the DeWalt brand name for it, but they're drills with a square grind on the end and a little bit of a pilot point in the middle. And these are awesome for clearing work out in preparation for a boring bar where you need a square bottomed hole. Looking inside, you can see how that drill has left a square shoulder, and then there's a dimple in the middle where the pilot point was, but that's further in and we don't care about that. I've measured the depth from the square shoulders, and now I can come in with the boring bar and square that up really easily, as opposed to using a regular twist drill, which leaves a giant 118-degree cone in the bottom of the hole that on a small bore like this can be very difficult to clean up with the boring bar. Then of course I come in with the small boring bar and bring this to final dimension, and also of course reacquire concentricity that's been lost by that drill. If you remember from the previous video, this is kind of a standard diameter that I just decided on. It was kind of in the middle of the range of a good work holding mandrel for the types of parts I want to make with this thing. So it's a 3/8 bore, and I'll turn a 3/8 mandrel on all of the part blanks that I want to use in this indexing head. Steady rest setups are actually always kind of neat, I think. There's something very mechanically pleasing about them. I don't use my steady a lot, but I've had to use it quite a bit on this project, so that's been fun. I'm feeling really good about that dimension. That seems excellent. Time now to Yahtzee this thing off. That's all the features I need to do in this single setup. I have some threads, both internal and external, to put on the other end, but the threads don't have to be perfectly concentric with all these other features. There's really no such thing as concentric threads anyway, because there's a lot of clearance in them, so I can part that off now and flip it around, where it'll be much easier to do the threads from the other end. I'm going to hold that in my forward jaw with some aluminum shim stock to protect that very hard-earned, flawless surface finish from the jaws. Then I dial that in. Good enough, I guess. This round-nosed tool is going to give me a little thread relief at the base of where the thread is going to end up, the external thread that is. This is again the M12 preloading thread for the spindle that holds it in place. As for cutting this thread, because I'm lazy and stupid, I thought I'll just do this with a die. I have the die and it'll be quick and easy. It's an easy setup that way, and this thread doesn't have to be machinist perfect, so a die should be fine, except that I seem to always forget that the larger a die is and the coarser the thread is, the higher the tool pressure is on that die. And the tool pressure on an M12 175 die is extremely high, much higher than this setup can tolerate. Because I'm holding the part with a small 4-jaw chuck and there's aluminum shim stock in there and probably some cutting oil got in there, the grip was nowhere good enough to stand up to this die, and it was just slipping in the jaws. I avoided this as long as I could, but I had to put on my big girl pants and blow the cobwebs out of the single point thread cutting part of my brain. I don't do very much of this because I mostly work on small things, and dies are a lot easier and just as good for most things on small parts. But in this case, single pointing was necessary. I'm using the method where you keep the half nut engaged and power the lathe back and forth, partly because it's quicker and easier on a short thread like this, but also because my lathe has an imperial lead screw, so you get more accurate metric threads if you leave the half nut engaged. Aside from one little boo-boo that you saw in the cold open that didn't cause any problems because it was early enough that I just kept cutting and the boo-boo was erased, but that went really well. First test fit now, and that's a little snug, but I think that's just burrs, so I'll do some cleaning up on this. I started with a Kratex bar to remove any burrs and clean up any jaggedy edges. The thread is a little bit woolly because this is 1018 steel, and 1018 honestly doesn't single point thread very nicely, but little Kratex, little emery, and I made it presentable. And that is now functioning beautifully. That's definitely a machinist thread. That's very close fitting. No play in that at all, which is kind of satisfying. I'm sure that won't cause any problems. Put a civilized chamfer on the end of that, of course. Then we need to do an internal M61 thread, and this is for the little cap screw that holds the crank handle onto the end of the shaft. Again, I'm just copying the end of the Vertex rotary table crank. All done with that setup now. That worked really well, just holding it inside the forge jaw like that. The shaft was long enough that I was able to hold on to the diameter in the middle, and that collar was just hanging out inside the chuck. Now for the work holding set screws, I'm going to use a V-block because I don't have a collet this size. I can drill the two opposite set screws all the way through, straight across, and my tap is conveniently long enough to do the same, tap straight through all the way across. But I do need to now index 90 degrees to do the other pair of holes, so for this I will use the Rose Index. Another tool that's getting a strangely large amount of use on this project. I've had this thing literally for years, and I don't often use it, but every so often it's a real lifesaver, such as when you need to index a round part that you don't have a collet for. Next, some flats go on the other end for the crank handle, and once again, 180 degree indexing required, Rose Index for the win. These flats allow the crank handle to create the turning moment on the shaft and also allow it to slide forward and aft to align with the correct radius of holes that you need in the indexing plate. There's the final shaft. It's looking very beautiful, if I do say so myself. Now let's see how good a fit I managed to achieve. And oh boy, oh that's lovely. That, let me tell you, 30-40 minutes of emery time is really worth it because that is really incredible. The finish on it is spectacular, and that spins beautifully in there. There's zero play in it. Really, really happy with that. Let's get the accoutrement on the other end and see how I did. I already know this stuff fits because we tested it last time, but now I can get the crank handle on there and see if it's all going to come together the way it's supposed to. Now here's that tensioning nut that I mentioned I was going to use. I wanted to use an M12 nylock for this. The nylock will allow me to set a little bit of preload on the shaft, and yeah, well, it turns out nylock nuts are designed for crappy hardware store bolts that have a lot of slop or a lot of clearance in them. And when you try to put them on a machinist thread, you have to carve a bunch of the nylon out of there. But that did work, and actually that's working really well. I can eliminate all the end float in that without compromising its free spinningness at all. So let's get the handle on there now. I knew I was going to have to turn down that nut a little bit, but oh, yeah, this is actually much worse than I thought. That handle doesn't come anywhere close to reaching the index plate. Something's very wrong here. I put an indicator on that and measured how far off it is, and it's very suspiciously 242 thousandths, which is awfully close to 1/4 of an inch, which suggests human error in my design, and by human I mean me. I'm not 100% certain what went wrong here, but this is my best guess. I measured the center crank axle separately from the outer bushing that's supporting it, and this center area where the preloading collar is, I think I double counted that. I think I included that area in both measurements. So that area ended up on the end of my bushing and in this area here on the end of the axle. Now, I think, however, I can still make this work. If I shorten the axle by the amount that it's too long, and then I push those other features in, that's the internal thread and the crank flats, That should leave me just enough room to get a custom-made collar in there that will thread onto what's left of the threads and lock in place with a set screw and do that preloading job instead of the nylock nut. I don't know if this is going to work because there's going to be very little of that thread left, and I can't add any more threads because what's left of the shaft is now occupied by the thread relief. If I'd used a fine pitch thread like I should have, this would be no problem. As it is, I'm going to have about 1.5 coarse threads, but I might get away with that, and it's easy to try making this collar and see, so let's do that. I made the aforementioned modifications to the shaft to push all of those features in by what would be 242 thousandths, but I went all the way to 250 just to give a little bit of spring preload on that indexing pointer, and that is looking actually really good. That reaches the plate now, and the preload on that pointer feels about right. It's easy to pull out, but it's still seated firmly, so I think that's really good. Now I can measure that gap and see how thick this collar needs to be, and interestingly, it came out to exactly 3/16. These are all metric parts, but a lot of imperial dimensions are showing up. I don't know why. So this is the little collar. I just tapped that with the inappropriately chosen M12 175 thread. And then there's that little locking screw that's going to do the actual work of holding it in place. The threads are fairly decorative at this point. Yahtzee. You can see I managed to get 1.5, maybe 2 threads on there, but it's enough to thread that on there and lock it in place with that little set screw. That eliminates any end float and leaves it free spinning, so that seems to be working well. I'll double check that the handle still fits now, see if I did the math right there, and oh, that's excellent, yeah. So I think we got away with that by the skin of half of an M12 thread. Just barely worked. If you grab this design off my Patreon to build it yourself, I did put a fine pitch thread in the CAD model and I corrected this 1/4 inch error. All right, let's get this on the shaper now. I've got enough parts to give it a test run. So I dialed that in square to the machine, which I'm happy to say was super easy to do, which speaks to a high quality reference surface. That's good, something went right. I turned up this sample workpiece, which is pretty representative of what I want to do. It's got the standard mandrel diameter on one end, and then the small end is kind of the smallest diameter part that I probably might want to use this for. Smaller diameters are a little trickier for rigidity, so I thought I'd try this. The idea is the part is extra long so that there's tool runout room for the shaper, and then you would part it off on the lathe to desired thickness. And that seems to be working well so far. I'll lock that in with all of the set screws. Let's imagine this is going to be a spline or a scalloped knob or something. I've got a round nose tool in there, and I've centered it up using the old balance of scale trick, which will be plenty good enough for this little test. I'll set up my indexing, and let's start taking some chips and see what happens. I'm just going to go 1 chip and see what happens. Obviously, I've already verified the stroke limit is set correctly, so it won't crash into anything. And that first chip went pretty good. Let's take another one. Oh, pretty good. So I just started doing a series of cuts, moving down a little bit at a time and then indexing around. But so far, seems to be going really good. Look at that. Now the limit of rigidity here is the workpiece itself because it's so small. So this is definitely not a test of rigidity of the overall fixture because it's obviously limited by a 1/4 inch diameter of brass. I did experiment with depth of cut though, just to see what this can handle. And obviously on heavier cuts, it does want to chatter. But the nice thing about the shaper is that light cuts don't really cost you any work because the machine is doing all of the cutting back and forth for you. It's not like on the mill where light cuts are a pain because you have to crank everything back and forth and constantly adjust the height yourself. The shaper does all that work for you. It's just a couple extra strokes to take light cuts. As I gained confidence with the setup, I tried leaving it running and feeding down while under power, which is normally what you do when you cut vertically with the shaper, and that went really well as well. Nice and smooth, very quick and easy. I gotta say, this seems to be working really well. I did a full lap of the part, and let's get this out of here and see how it looks. Look at that, isn't that nice? I mean, sorry to toot my own horn, but I think that came out great. I'm very, very pleased with that. The indexing seems to have gone perfectly. I don't know if you can tell on camera, but obviously in the areas where I took too heavy of a cut, there are some chatter marks in there, but when I found the right cut depth for this setup and this material, then it left a beautiful finish in there. Yeah, very, very nice. Well, I think I'm sufficiently confident this thing works that I can finish all of the finishing work, as it were. I machined the remaining sides of that frame that I'd left bandsaw cut. I also filed down all of the welds to make those look as nice as I can. Then I powder coated the thing to make it look nice and protect it. I went with blue because it's the only powder coat I have that isn't black, and I'm tired of black. The precision surfaces were all masked off with Captain Tape. Obviously, I don't want powder coat on my reference surfaces. Captain Tape works great for that when powder coating. Can take the heat no problem. Now it's time to install the main bearing or bushing thingamajig in the middle permanently. So that got a thorough cleaning and degreasing, and that's going to be held in with Loctite 680. There's no need for this to ever come out again, so I didn't see any point in making some sort of complicated retaining system. And no, you almost put it in backwards. Shut up. Also, fun fact, this footage caught the moment my glasses broke. All sorts of fun things happen when you video every single thing you do. And of course, the indexing plates go on the back, as you've seen me do many times at this point. Note that the set screw had to be shortened on that locking collar because all of the indexing stuff has to slide over it. That was a little tricky thing. Well, there it is, the final indexing fixture for my shaper. I'm quite confident this thing works. I'm very pleased with the test results so far. And you're going to be seeing this on some real parts coming up real soon on the channel. Probably first on the locomotive. I've got a ratchet wheel that I need to make for that for the mechanical lubricator. That's going to be fun. Thank you so much for watching. Thank you so much to my patrons who make all of this content happen. And I will see you soon.